When we place a drop of juice onto a small glass prism and hold it toward the light, it feels simple. A line appears, a number shows itself, a measurement is made. But that small moment connects us to a scientist working in the 1800s, long before handheld tools, long before industrial agriculture, trying to solve a practical problem. His name was Adolf Ferdinand Wenceslaus Brix. He was born in 1798 in Germany, during a period when science, chemistry, and industry were rapidly advancing. Europe was moving into a more industrial era. Trade was expanding, sugar production and brewing were becoming more standardized and commercialized. And standardization was the key. At that time, sugar refiners and winemakers needed a reliable way to measure the concentration of sugar in liquids. Sweetness determined value. Alcohol production depended on it. Inconsistent batches meant economic loss. Before precise instruments, producers relied heavily on taste, density estimates, and experience. But taste varies. Temperature affects density, and experience, while valuable, is difficult to standardize across regions and industries. Adolf Brix worked to solve this. He studied how dissolved sugar changes the physical properties of water, particularly its density. Through careful experimentation, he helped develop a standardized scale relating the percentage of sucrose in a solution to measurable physical characteristics. The unit that bears his name, the degree Brix, represents 1 gram of sucrose dissolved in 100 grams of solution. In practical terms, 1 degree Brix equals 1% sugar by weight. This created clarity. It allowed sugar producers and winemakers to communicate precisely. It allowed consistency across shipments and seasons. Originally, measurements were commonly made using hydrometers, instruments that float in liquid, to measure density. But alongside developments in density measurement, another scientific field was advancing: optics. Scientists had long known that light bends or refracts when it passes from one medium into another. When light moves from air into water, it changes speed and direction. Add sugar to that water, and the light bends differently. The more dissolved solids in the liquid, the greater the change in refraction. This principle led to the development of the refractometer. A refractometer uses a prism to measure how much light bends when passing through a liquid sample. When a drop of juice is placed on the prism, light enters and refracts. Inside the instrument, a boundary line forms between light and dark. That line corresponds to a scale, often calibrated directly in degrees Brix. What once required laboratory conditions eventually became portable. By the 20th century, handheld refractometers were widely used in vineyards, orchards, and processing facilities. Winemakers adopted Brix readings to determine optimal harvest timing. As grapes ripen, sugar accumulates. Measuring Brix helps estimate potential alcohol levels and desired flavor balance. Fruit growers use Brix readings to assess sweetness and maturity. Maple syrup producers use it to ensure proper sugar concentration. Honey producers use refractometers to evaluate moisture content. What began as industrial chemistry became an agricultural tool. Over time, Brix readings took on additional meaning. Because sugars in plants are produced through photosynthesis, and photosynthesis depends on plant health, some growers began observing patterns. Healthy soil supports healthy roots. Healthy roots absorb balanced minerals. Balanced minerals support efficient photosynthesis. Efficient photosynthesis increases sugar production. In many cases, higher Brix readings coincided with improved flavor and stronger plant resilience. It is important to be precise here. Brix measures dissolved solids, primarily sugars. It does not directly measure total mineral content, vitamin levels, phytonutrients, or protein. However, sugar production is part of a plant's metabolic process, and plant metabolism is influenced by soil biology, mineral availability, sunlight, and stress conditions. So Brix became one observational metric among many. It's not the whole story, but it is a signal. And today, that signal may be more relevant than ever. We live in a time when food is abundant, but questions about nutrient density are increasing. Many people sense that food does not always taste the way it once did. Fruits can look beautiful, but lack depth of flavor. Vegetables can appear perfect, yet feel flat. Modern supply chains prioritize uniform appearance, shelf stability, transport durability, and yield per acre. But appearance and yields do not necessarily reflect nutrient concentration. As consumers, we ultimately rely on our senses. Smell tells us something. Taste tells us something. Cravings can tell us something. Traditional cultures trusted these senses deeply. But in a complex food system where produce may travel thousands of miles and be grown in depleted soils, having an additional tool can be helpful. A handheld refractometer is now affordable and easy to use. A consumer can squeeze a drop of juice from a tomato or orange, place it on the prism, look toward the light, and observe the Brix reading. Higher Brix often corresponds to sweeter flavor, but it may also suggest more active photosynthesis during growth. Does a higher Brix guarantee superior nutrition? No. But when comparing similar foods, 2 tomatoes, 2 melons, 2 apples, it can provide additional information. It becomes a way of asking, how did this plant grow? What was happening in its soil? What level of metabolic activity occurred during its development? Used thoughtfully, a refractometer can help consumers learn which farms, markets, or growing methods consistently produce more flavorful food. And flavor matters. Flavor often correlates with complexity. Complexity reflects balanced plant metabolism. Our senses remain primary. Taste and smell evolved to guide us, but pairing those senses with measurement creates an interesting partnership. Observation plus data. Experience plus light. In some ways, this brings us back to Adolf Brix. He was not trying to revolutionize agriculture. He was solving a problem of standardization in sugar solutions. Yet his work gave us a unit that now fits in a pocket and invites us to pay closer attention to our food. The refractometer is a simple technology. No complicated electronics required, no elaborate setup, just light passing through liquid, and a boundary line appearing in response. In an age where food quality can be difficult to assess from appearance alone, that line offers a small piece of insight, not a verdict, but a clue, measured by light, interpreted through experience, integrated with our senses. Perhaps that is what makes Brix still relevant today, a 19th century scientific standard helping 21st century consumers ask better questions about food, not replacing intuition, but supporting it, because ultimately, the goal is not a number, the goal is nourishment, measured by life, revealed through experience.